Well, thank you so much for the introduction, Andrew. And hello, everyone. I'm Ryosuke Okuno from the University of Texas at Austin. And I'm currently leading Energi Simulation Industrial Affiliate program on carbon utilization and storage at UT Austin. So we cover a wide range of topics in carbon management value chains, starting from CO2 capture, CO2 conversion, CO2 sequestration as minerals, in situ, ex situ, and EOR. So we have this EOR/CCS/CCM. The CCM stands for CO2 capture and mineralization. So this is an emerging term I see in some places to differentiate from conventional CCS in aquifer. So for CO2 capture conversion research, we are focused on the new pathway in carbon management in which we capture CO2 as a bicarbonate using the tertiary amines, and we separate the resulting bicarbonate in an electrochemical way while regenerating amine without heating the solution. So this non-thermal process is expected to be more energy efficient than conventional CO2 capture process, and we are increasing the activity on this topic. And for other selected topic here, part of EOR research topics in our group, we have been working on steam solvent hybrid processes for bitumen recovery for the past 15 years. And one of the PhD student, Hassan, he has a good poster in which he shows the utilization of a new solvent to enhance bitumen recovery in Canada. And also another exciting project is a joint effort with Petrospec Engineering and also Dr. Kansas at the University of Calgary. We are trying to build a large-scale physical model that enables us to test the various solvent methods and solvent steam hybrid methods for bitumen recovery. And the facility will be located in Edmonton at the Petrospec Engineering. So that's another exciting topic in this category. And also, we are actively working on the various aspects of CO2 mineralization, or CCM, both in situ and ex situ. So CO2 mineralization reactions are complicated. So one limitation is rate limiting step of mineral dissolution that releases divergent cations in the aqueous media for the subsequent mineralization. And we are studying one way to enhance the kinetics and extent of mineral dissolution by ligands, such as sodium formate, as novel fluids. And two posters from Hao and Femi from our group have a good presentation in the poster on the successful experimental data of dissolution reaction enhancement by sodium formate solution. And also, Femi's poster explains the fundamental analysis using a geochemical modeling framework to understand the reaction pathways in this enhancement of basalt dissolution by sodium formate solution. So today's topic is aqueous nanobubble dispersion. This is one of the techniques that are applicable for both EOR and CCM, CO2 mineralization. And I presented the fundamental part of this topic last year, and I'm going to start by a brief overview of what I presented, going through key points, and then show some promising results for EOR and ongoing project for CCM using aqueous nanobubble dispersion of CO2. So I started by showing the snapshot of a high-pressure nanobubble sample in a sapphire cell. So interior volume is 15 cc. And the pressure here is 3,000 psi, and it looks like a clear ordinary water, but this contains the good amount of CO2 at the supersaturated state. And after depressurization, the volume expands to 630 cc from original 15 cc. And you see visible bubbles here and some gas cap that is connected to external the accumulator. after expansion. And after material balance, we can quantify it's actually 1.5 times the inherent solubility of CO2 in this water under high pressure. So, and then the movie here is one of the movies I showed last year. So this window width is 2 micron, and this particular sample have a very energetic Brownian motion of nanobubbles of a size around a few tenths of a nanometer. And the key point from last year was that what is making this supersaturation is nanobubble, but nanobubbles by themselves are not the main contribution to the gas content in the nanobubble sample. So supersaturation is basically the key word. And the fundamental data of thermodynamics of an aqueous nanobubble dispersion is the gas content. So here, y-axis is the CO2 concentration in nanobubble sample in mole per liter. And the horizontal axis is pressure, external pressure. And the red line is the inherent solubility of CO2, in this case, dear water. And black dots are experimental data of CO2 content in high pressure aqueous nanobubble dispersion. And as you see that enhancement by nanobubble is increasing with increasing pressure. And also enhancement factor somehow levels off at a certain pressure. In this case, perhaps 1500 psi. Above that, enhancement factor stays almost the same, which is 1.5 times. And we tested CO2 content in aqueous nanobubble dispersions for brines, different pH and different temperature. And somehow this factor 1.5 is a good estimation. So 1.5 times enhancement is like a magic number for CO2 nanobubble dispersion. CO2, not nitrogen and any other gases. For CO2, 1.5 is a magic number. So again, the supersaturation is a key word. So what's made by nanobubble is the supersaturation of the surrounding water phase by gaseous species. So here I'm showing a schematic of a spectrum of supersaturation level. Those supersaturation here is basically no supersaturation with the 2 bulk phases, bulk CO2 phase, and that is in contact with the aqueous phase at the CO2 solubility. And this is originally 2-phase system. And if you have a bubble, and depending on the size of bubbles, the supersaturation level changes because the capillary pressures are different. So we have a moderate supersaturation with slightly bigger bubbles than the one on the right. So here it's very tiny bubbles, and you expect a higher level of supersaturation. So if I get the magnified view for this aqueous sample on the left, you have molecularly dispersed CO2 in the water at the solubility level. And if I take a magnified view from the middle one, then you get bubbles here. I don't know how it works. Yeah, so here the bubbles. And the surrounding water phase are supersaturated by CO2 molecules, and that concentration of CO2 molecules in the aqueous phase is greater than the one here because it's supersaturated by capillary pressure. And then as expected, the bubble size increased capillary pressure, that in turn increased level of supersaturation. So that's what we are enhancing by using the nanobubble. So now let me talk about what the nanobubble does for enhanced oil recovery. So basically, based upon the properties I presented in previous slides, it is basically CO2 supercharged water. Right? So there are 2 hypotheses. One is that the miscible water injection is possible if enough CO2 is injected above MMP for the oil at the given temperature. So water is, of course, not miscible with oil, but CO2 in the nanobubble can be miscible with oil when it's injected above MMP. And then when the apparently stable nanobubble sample is injected into formation and then contact with oil, now CO2 in the water is even less stable because it wants to go to oil phase instead of being in the water phase. So that mass transfer of CO2 from water to oil is going to result in CO2 phase nucleation upon the displacement front. And then basically that is to locally activate the CO2 flood at the displacement front and then pushing oil ahead of it in a miscible way. And the CO2 phase nucleated is pushed by water. And then voidage caused by oil displacement by nicely filled by water injected as part of a nanobubble sample. So this is one of the hypotheses. We are testing this hypothesis in a series of experiments using live oil core floods with a high level of supersaturation by nanobubble, and analyzing it using a method of characteristics and other numerical simulation techniques. And the second hypothesis here is that the recovery of trapped oil by water is more efficient because sealing water is displaced in a miscible way with supercharged water by CO2. So this is different from the traditional WAG in which water and CO2 are injected as separate fluids. So when trapped oil is sealed by water, nanobubble can displace that sealing water in a miscible way. So nanobubble should have a greater access to the trapped oil. And this is also to help sweep efficiency, not only displacement efficiency. And based upon these hypotheses, we are studying different conditions for different reservoirs, for different operators. And the nanobubble can play an important role. For example, because it uses a small amount of CO2 than CO2 flood, we can make a more CO2 efficient EOR method. And for example, if net CO2 utilization was 6 MSCF per STB of oil, then it can be reduced by a factor of 3, resulting in 2 MSCF per STB. And so that changes also cost structures for other parts of OPEX in EOR. And for example, if a break-even of CO2 EOR was $40 per barrel of oil, then it can be reduced to $30 per barrel. And then also more opportunities of EOR. For example, tight oil EOR by nanobubble. I'm going to show some successful experimental result in later slide. And also regarding second hypothesis here, the new EOR opportunity might appear in residual oil zone or ROZ, where the water, the oil is naturally water flooded. And also, basically, we can increase more the oil recovery per unit amount of CO2. So in the future, when captured CO2 is utilized for EOR purposes, it's very important to increase CO2 efficiency in EOR. So the nanobubble technology might be promising when captured CO2 is utilized for EOR. So now let's talk about some experimental data. So we tested the nanobubble and compared it with CO2 in half and puff of live oil in tight sandstone. So this formation had a temperature of 102 degrees Celsius, and we prepared the live oil, and the core utilized for the experiment were Kentucky sandstone with a permeability of 0.6 millidarcy and a porosity of 15%. And the reservoir brine was 66,000 ppm hard brine. And in half and puff, the pressure for injection and soaking was 4,500 psi, and production pressure was 3,500 psi. And based upon the PVD data, as you see here, the swelling data, we calibrated the equation of state, and then they predicted the thermodynamic MMP with oil. And the CO2 at the given temperature was 2,500 psi. So half and puff pressures were above the MMP. So this is a nanobubble of CO2 above MMP. So here's the result. So y-axis is a cumulative improved oil recovery, and the horizontal axis shows different cycles in the half and puff. And blue one is a supercritical CO2 case, and orange one is a CO2 nanobubble. And before these cycles, we had a brine injection, soaking, and production. And after that, first cycle started. And you see here, the first cycle especially, the nanobubble case resulted in almost twice the oil recovery in comparison to supercritical CO2 case. And systematically, nanobubble enhanced oil recovery than the CO2 case. And also, amount of CO2 utilized for nanobubble case is perhaps less than 20% of the CO2 case. So less CO2 is used for greater amount of oil recovery. And of course, we need a more test, but this is a promising result showing 40% enhancement of oil recovery in comparison to CO2 case after fourth cycle. So I set the factor of 3 for the reduction of CO2 utilization in comparison to pure CO2 injection. And here's my fundamental reasoning. So figure on the left is a CO2 molar density in mole per liter in pressure and temperature space. And here you see a vapor pressure of CO2 and a critical point. And the numbers inside of the figure are CO2 molar densities. For example, the reservoir temperature pressure of 2500 psi and 160 Fahrenheit gives 10 mole per liter. So under this condition, 1 liter of pore space is occupied by 10 moles of CO2 as a pure CO2. And then if we use a nanobubble with a CO2 content of 3 mole per liter, then same 1 liter of pore space is occupied by nanobubbles that contain only 3 mole of CO2 in comparison to 10 moles of pure CO2. So that's why we can reduce 70% of CO2 to displace resident fluid to fill the voidage in oil recovery. So if we assume $30 per ton of CO2 and 6 MSCF of CO2 per STB as a CO2 utilization, then this means the cost reduction from $10 per SCF to $3 of CO2 per STB. So this is a cost reduction for only CO2, but this reduced amount of CO2 used in this CO2 EOR resulting also reduced other operation costs, such as gas compression and also recycling of a breakthrough gas. So here's a potential cost structure just as an example. So y-axis is dollar per barrel, and the horizontal axis shows 3 cases. First case on the left is a CO2 EOR, assuming $40 per barrel as a CO2 EOR cost, and 10% of it is CO2, and the other $30 was $10 out of $40 is CO2, and $30 are other OPEX. And if we assume nanobubble with operation cost reduction of 20% and CO2 utilization reduction by a factor of 3, then this $40 becomes less than $30. And this is called a conservative scenario in which we do not assume any enhancement in oil production in comparison to CO2. But if we assume enhancement of oil production in comparison to CO2, as you saw in the half and puff experimental result, basically this denominator on the y-axis will be greater than 1. So you divide this bar by a factor, enhancement factor of oil production, in this case 1.4, then the total cost will be close to $20. But again, we need more experiments and see if nanobubble can reduce cost while increasing oil production also. And as I said at the beginning, CO2 nanobubble is promising also for CO2 sequestration, particularly CCM, in which CO2 and the water are co-injected. And widely known process or project is the one in Iceland, Carbfix. So they inject the CO2 and the water as carbonated water. And so this is a snapshot of the first web page in their website, and they are updating this number every day. So you can check how much CO2 had been injected since 2014. So they are injecting carbonated water at the solubility, like 0.9 mole per liter, based upon their data. So limitation is, of course, the CO2 content in the injection water that directly affect the operation cost, dictated by water throughput in the process. So nanobubble can enhance the CO2 content in injection water, which reduces the operation cost. And also, we observed in published and also unpublished data from our group that nanobubble can enhance the kinetics and extent of mineralization process of CO2 in mafic and ultramafic rock samples, like basalt and peridotite. So mineralization reactions are quite complicated. At least we need 2 steps. First step is a dissolution of metal silicates that releases divergent cations like calcium, magnesium in the aqueous media. And then those metal ions are going to be reacted with the carbonate that is originated from injected CO2. So these 2 processes are important. And many papers show the first step, dissolution of metal silicates, is going to be a rate limiting step. And yeah, so as I said, we are studying different ways to accelerate and increase the extent of reactions of the both steps in different ways. And nanobubble is one of them. And we have an active project with a CO2 mineralization company operated in Oman and the UAE. And I was actually in Oman 2 weeks ago. And a special thanks to 44.01 to host us for the visit and the field trip. So I'm showing here a very beautiful country, Oman, and the peridotite-rich mountain. And I was there and to observe mineralization through the fractures in the outcrop. So you see this water bottle. So you see how thick these carbonates can be through the fracture in this very reactive alkali rock. And with that, I'd like to thank all the sponsors for our research team, and we'll be happy to answer any questions you may have.
Thank you, Dr. Okuno. Questions from the floor? Not yet. There's one online here. I need to ask the anonymous attendees to reveal himself or herself, otherwise I may not be asking a question. There's no follow-up. But anyway, if nanobubbles are in the water phase, does it not decrease its viscosity and make the mobility ratio worse for the oil-water EOR system?
Good question. So we tested apparent viscosity in core floods, where we displaced the resident brine, stirred brine in the core by the nanobubble that was prepared using the same brine, and calculated the apparent viscosity of the nanobubble, and we observed a 5 to 7% increase in viscosity in comparison to stirred brine. And I think that is because of those basically particles as bubbles in the water phase that is slightly increasing viscosity. So that's a high temperature pressure measurement using porous media. And also related question to that is shear stability of nanobubbles through the porous media. And we observed the effluent sample was still nanobubble, even after the flooding. So that's maybe most relevant data as an answer to the question.
Okay. Actually, I follow up about your shear stability. Recognizing the heterogeneity in the reservoir, how tolerant is that nanobubble before it actually would disintegrate and becoming separate again, like in actual real-life examples, under reservoir conditions and pressure and pH and salinity? You're going to be doing some work, lab work around that or what?
Yeah, so the stability of nanobubbles in porous media after being injected, right? That's the question. So for EOR, interestingly, we are not interested in stable nanobubble. As I mentioned in some of the slides, we'd like to activate locally the CO2 flood, in which CO2 become less stable when it's exposed to oil. And the CO2 goes from water phase to oil phase. So in that sense, for EOR purposes, we are not interested in making nanobubble stable in the long term. So, but for mineralization, yes, we would like to make sure it doesn't generate a bulk CO2 phase.
Okay. Yeah, okay, this is from Ali Papi. Hi, thanks for the great presentation. Now, as you mentioned correctly, the CO2 mineralization remains limited due to an equilibrium reached after a while of exposure to brine. How would you think of this issue, and how do you think this method can improve the dissolution of CO2 in the brine and mineralization?
The question is how CO2 nanobubble is going to help dissolution and mineralization of CO2.
Right, okay.
So the concept is that we inject the CO2 in a dissolved form. So we don't have to wait for CO2 to dissolve in water, unlike traditional CCS using CO2. And for CCM, the target formations are expected to be reactive, like mafic, ultramafic rock formations. So it's very different from CCS in aquifer, like traditional sandstone aquifers. So we inject CO2 in a dissolved form, and we expect CO2 to be consumed in reaction as soon as conditions are met. So.
Okay. Next one from Mohammed Rask. At reservoir scale, what are the challenges of modeling nanobubble injection, for instance, in terms of Reddit perm?
Very, very good question. So that's active research topics we are working on. And also simulation technologies for nanobubble processes. So at the moment, we are preparing papers based upon experimental data and history match simulation. So maybe next year I'm going to present that in some way, poster or presentation. So at the moment I wouldn't be able to disclose it, unfortunately. So
okay, you got to pay to get the answer, I guess. Next one is from Jessica Peralta. How do you think that this technology perform with foamy oil?
So is the foamy oil referring to heavy oil in Canada?
I imagine, yes.
Very interesting. So it's different from the nanobubble we are working on. So this is the aqueous nanobubble, and surrounding phase is the water, aqueous phase, polar phase. And the foamy oil is actually oleic nanobubble. So it's a very different system, and we haven't, to be honest, we haven't explored that part of the nanobubble. But I know several people are making oleic nanobubble to decrease carbon intensity of gasoline combustion, where they make a hydrogen nanobubble in gasoline. So, but you can imagine it's a very dangerous experiment. So we haven't done yet. So.
Okay, Casey, you got a question?
Yeah, thank you for your presentation. My question is that your operating cost, does it include the cost of generating these nanobubbles, or is it very costly to do that?
So the nanobubble dispersion we are preparing or generating at the scale does not require any additives such as a surfactant, polymer. It's just physically supersaturating. And what we need is some mixing processes And we are working on different ways of nanobubble generation at the steady state for large-scale deployment. And that part is, unfortunately, under NDA,
Here's another one.
so confidentiality agreement. So I wouldn't be able to disclose the details of the generation procedures.
Okay, so once again, thank you, Dr. Okuno.